Download this code from codegive.com, link in the description below. OK, let's dive deep into Bloom filters. This comprehensive tutorial will cover the theory, implementation, variations, and considerations for using Bloom filters effectively, along with practical Python code examples. What is a Bloom filter? A Bloom filter is a probabilistic data structure used to test whether an element is a member of a set. Crucially, it's designed to provide a very space-efficient way to do this. The key characteristic: false positives are possible. The filter might tell you that an element is probably in the set, even if it isn't. False negatives are impossible. If the filter says an element is not in the set, you can be absolutely certain it's not there. Think of it as a highly efficient way to rule things out. It's often used in situations where quickly rejecting a large number of items that are not present is valuable, even if it occasionally makes a mistake and says something is present when it isn't. Why use Bloom filters? Space efficiency. Bloom filters use significantly less memory than storing the entire set directly, especially when dealing with a large number of elements. This is because they only store bit flags, rather than the actual elements themselves. Speed. Membership tests are very fast, usually requiring a fixed number of hash function calculations. These operations are generally O, K, where K is the number of hash functions. Simplicity. The core algorithm is relatively simple to understand and implement. Use cases. Bloom filters are valuable in a wide variety of applications. Spam filtering. Check if an email address or URL is on a blacklist. Database systems. Optimize database queries by preventing lookups for keys that are definitely not in the database. Pre-filtering before accessing disk. Network caching. Determine if a resource is likely to be in the cache. Content delivery networks, CDNs, determine if a particular object is likely to exist at an edge server. Cryptocurrency mining. Quickly check for duplicate transactions. Recommendation systems. Filter out already recommended items. Big data analytics. Reduce the amount of data that needs to be processed by filtering out records that don't meet certain criteria. How Bloom filters work, the core concepts. 1-bit array, Bloom filter. The foundation of the Bloom filter is a bit array, a simple array of bits, initially all set to 0. The size of this bit array is m. 2 hash functions. You need k independent hash functions. Each hash function takes an element as input and produces an integer value between 0 and m1, an index into the bit array. Crucially, these hash functions should be as independent and uniform as possible to minimize collisions and reduce the false positive rate. Good choices are often variations of murmur hash, FNV hash, or using multiple distinct solved values with a single hash algorithm. 3. Insertion. To insert an element into the Bloom filter. 1. Pass the element to each of the k hash functions. 2. For each hash function output, take the modulo by the array size, m, to get an index within the bit array. 3. Set the bit at that index to 1. 4. Membership test. To check if an element is potentially in the set. 1. Pass the element to each of the k hash functions. 2. For each hash function output, take the modulo by the array size, m, to get an index within the bit array. 3. Check if the bit at each of those indices is set to 1. 4. If all of the bits are 1, the Bloom filter reports that the element is probably in the set. If any of the bits is 0, the element is definitely not in the set. Visual example. Imagine a Bloom filter with m equals 10, bit array of size 10, and k equals 3 hash functions. 1 initial state asterisk. 2 insert apple asterisk. Asterisk hash function 1, apple, dash 2. Asterisk hash function 2, apple, dash 5. Asterisk hash function 3, apple, dash 7. 3 insert banana asterisk. Asterisk hash function 1, banana, dash 0. Asterisk hash function 2, banana, dash 3. Asterisk hash function 3, banana, dash 7. 4 check if apple is present asterisk. Asterisk hash function 1, apple, dash 2, bit at index 2 is 1. Asterisk hash function 2, apple, dash 5, bit at index 5 is 1. Asterisk hash function 3, apple, dash 7, bit at index 7 is 1. All bits are 1, so the Bloom filter reports that apple is probably in the set. 5 check if orange is present asterisk. Asterisk hash function 1, orange, dash 5, bit at index 5 is 1. Asterisk hash function 2, orange, dash 1, bit at index 1 is 0. Asterisk hash function 3, orange, dash 4, bit at index 4 is 0. Because the hash functions did not hit only 1 bits, the Bloom filter reports that orange is definitely not in the set. 6 check if grape is present asterisk. Asterisk hash function 1, grape, dash 0, bit at index 0 is 1. Asterisk hash function 2, grape, dash 5, bit at index 5 is 1. Asterisk hash function 3, grape, dash 7, bit at index 7 is 1. All bits are 1, so the Bloom filter reports that grape is probably in the set. However, grape was never inserted. This is a false positive. Python code example, basic implementation. Explanation of the code asterisk. Asterisk underscore underscore init underscore underscore, self, capacity, error underscore rate, asterisk. Asterisk initializes the Bloom filter. Asterisk capacity, the expected number of elements to store. Asterisk error underscore rate, the desired false positive probability. Asterisk calculates the optimal size of the bit array, self.size, and the number of hash functions, self.number underscore hashes, based on the capacity and error underscore rate. These calculations are key to balancing space efficiency and accuracy. Asterisk creates the bit array, self.bit underscore array, and initializes all bits to 0. Asterisk underscore calculate underscore size, self, asterisk. Asterisk calculates the optimal size of the bit array, m, using the formula m equals, capacity asterisk ln, error underscore rate, slash, ln, 2, caret 2. This formula is derived from the analysis of Bloom filter false positive probabilities. Asterisk underscore calculate underscore number underscore hashes, self, asterisk. Asterisk calculates the optimal number of hash functions, k, using the formula k equals, m slash capacity, asterisk ln, 2. Asterisk underscore hash, self, item, seed, asterisk. Asterisk hashes the item using a cryptographic hash function, SHA-256 in this example, combined with a seed value. The seed value is important to create multiple independent hash functions. Asterisk the result is taken modulo self.size to ensure it falls within the bounds of the bit array. Asterisk insert, self, item, asterisk. Asterisk inserts an item into the Bloom filter. Asterisk iterates self.number underscore hashes times, once for each hash function. Asterisk calculates the index using self underscore hash, item, I. Asterisk sets the bit at that index in the bit array to 1. Asterisk underscore underscore contains underscore underscore, self, item, asterisk. Asterisk checks if an item is potentially in the Bloom filter. Asterisk iterates self.number underscore hashes times. Asterisk calculates the index using self underscore hash, item, I. Asterisk if any of the bits at the calculated indices is 0, the function immediately returns false, the item is definitely not in the set. Asterisk if all of the bits at the calculated indices are 1, the function returns true, the item is probably in the set. Choosing m, bit array size, and k, number of hash functions. The choices of m and k are crucial for optimizing the Bloom filter's performance. They affect the false positive rate and the space requirements. Asterisk larger m, bit array size reduces the probability of collisions, leading to a lower false positive rate, but requires more memory. Asterisk larger k, number of hash functions initially decreases the false positive rate, but after a certain point, it can increase the false positive rate because more bits are set to 1, leading to more collisions. The formulas used in calculate size and calculate number hashes in the code are derived to provide near optimal values for m and k given the desired capacity and error rate. These formulas aim to minimize the false positive rate for a given space usage. Formula derivation, briefly. The probability that a bit is not set after inserting n elements, using k-hash functions, into a bit array of size m is. Therefore, the probability that a bit is set is. The probability of a false positive, all k bits being checked are set to 1, even if the element is not in the set, is. To minimize the false positive rate, you differentiate this expression with respect to k and set the derivative to 0. Solving for k gives the optimal number of hash functions. Substituting this optimal k back into the false positive probability equation and solving for m given the desired false positive rate gives the formula for the optimal bit array size. Improving the hash functions. The quality of the hash functions is paramount to the performance of a Bloom filter. Ideally, you want hash functions that are uniform. Each hash function should distribute elements evenly across the bit array. Independent. The outputs of different hash functions should be uncorrelated. This is difficult to achieve perfectly, but using different hash algorithms or different seeds with the same algorithm helps. Fast. Hashing should be computationally efficient, as it's performed for every insert and lookup. Common techniques for generating multiple hash functions. One-seeded hashing. Use a single hash function, like SHA-256, murmur hash, FNV hash, with different seed values for each hash function. This is the method used in the provided code. Two double hashing. Use two independent hash functions, h1, x, and h2, x, and generate subsequent hash functions as. This is a good approach because it only requires two independent hash functions. 3 chaining hash functions. Use the output of one hash function as the input to the next. This method can introduce correlation if not done carefully. Example of double hashing. Bloom filter variations. 1 counting Bloom filter. Instead of a bit array, it uses an array of counters. When an element is inserted, the counters at the corresponding indices are incremented. This allows you to remove elements from the Bloom filter, by decrementing the counters. However, counting Bloom filters require more memory and are subject to counter overflow if insertions/deletions are frequent. 2 scalable Bloom filter. Dynamically adjusts its size as the number of elements increases, maintaining a target false positive rate. When the filter reaches its capacity, a new, larger bloom filter is created, and the old filter is kept. Queries check both filters. This avoids the need to predefine the exact capacity. Usually implement as a list of bloom filters. 3. Cuckoo filter * an alternative to bloom filters that provides similar functionality but often achieves lower false positive rates and supports deletion. It uses multiple hash functions and an associative array to store fingerprints of elements. 4. Quotient filter * another alternative data structure for approximate set membership testing. It's based on representing the quotient and remainder of hash values. Quotient filters can provide better space efficiency than bloom filters in some scenarios and offer advantages for locality and clustering. Considerations and trade-offs * false positive rate * the primary trade-off is between space efficiency and the false positive rate. A smaller bloom filter will have a higher false positive rate. Memory usage * bloom filters are very space efficient but still require memory for the bit array. The size of the bit array depends on the capacity and desired error rate. No deletion. Basic bloom filter Standard bloom filters cannot delete elements. Once a bit is set to 1, it remains 1, even if the element that caused it to be set is removed. Counting bloom filters address this but introduce their own complexities. Hash function quality * poorly designed hash functions can significantly increase the false positive rate and negate the benefits of using a bloom filter. Dynamic capacity * if the number of elements you need to store changes significantly over time, consider using a scalable bloom filter. Alternative data structures * consider cuckoo filters, quotient filters, or other approximate membership data structures if you need features like deletion or have specific performance requirements. Choosing between data structures. Bloom filter * use for large data sets, high insertion rates, and when deletions are not needed or infrequent. Good for quickly filtering out negative results. Counting bloom filter * use when deletions are needed, but be mindful of memory usage and potential counter overflow. Cuckoo filter * good alternative to bloom filters, often achieves better performance and supports deletion. Can be more complex to implement. Quotient filter * offers space efficiency and advantages for locality, good for scenarios where clustered data is important. Can have complex implementation. Set, hash set / dictionary use when the number of elements is relatively small, you need exact membership testing, no false positives, and you require deletion or other operations beyond simple membership testing. Sets generally consume more memory than bloom filters for the same capacity. Conclusion. Bloom filters are a powerful and versatile tool for approximate membership testing. By understanding the underlying principles, trade-offs, and variations, you can effectively apply them to a wide range of problems where space efficiency and speed are critical. This tutorial should provide a strong foundation for implementing and using bloom filters effectively in your projects. Remember to carefully consider the specific requirements of your application when choosing the optimal parameters and data structure.